Now we will try to understand the basics of two types of curvilinear coordinates. Now there are some problems in physics for which the traditional choice of Cartesian coordinates is not useful, and we have to go for other types of coordinates. The coordinates which correspond to this type of system are basically having two types categorized as r theta phi, called as spherical polar system, and the other type, which is the S phi z system, is called as cylindrical system of coordinates. So we will look into these two one by one, how these are linked to the traditional Cartesian systems, what are the limits on these variables or coordinates, that is the values or the range of values that these coordinates can take. As far as Cartesian is concerned, we know that all of them x, y, z can range from minus infinity to plus infinity. But this is not true for the other two cases. So let us first look into spherical polar system. So you can always draw it on a Cartesian system. Suppose this is the point P having coordinates x, y, and z, and we know that how we reach to P is we travel a path x along x-axis, then a path y along y-axis, and then path z along the z-axis to reach point P. So we call it as point P having coordinates x, y, and z. So we start with the origin and we draw a straight line directly joining the points O and P, and we label it as R. Now the projection of this R over the z-axis, let us call this as theta. Now this projection is just going to be R cos theta. So the other projection is going to be R sin theta. Now let us just label the other angle as phi, angle lying in the xy plane. Now since this is R sin theta, this component is going to be R sin theta into cos phi, and this component along y-axis is going to be R sin theta into sin phi. So we have already defined the coordinates. As we can see, the equations which relate this R theta phi to the Cartesian coordinates x, y, z are straight away clear, that x is R sin theta cos phi, the coordinate y is R sin theta sin phi, and the coordinate z is just R cos theta. So once we know x, y, z, we can directly shift to the R theta phi system or vice versa. So from this diagram we see that this R can range from, suppose this point P is sitting on point O. In that case value of R is just 0, and if this point P moves very far away, in that case the value of R is infinity. Now this phi can keep on circulating in this xy plane. So starting from 0, the maximum value of phi is just going to be 2 pi. So the limit over phi is from 0 to 2 pi. Now we have already covered this entire plane. So value of theta it starts from z axis where the value of theta is 0, and it ends up at the negative z axis, and the angle covered by theta reaching the negative z axis is just pi. So these are the limits on these three coordinates. We know that in Cartesian system we define dl bar as dx x cap plus dy y cap plus dz z cap. Similarly, we can define the line element dl bar here as well as say dlr, so this is r component of L, into r cap plus dl theta theta cap plus dl phi cap. Note that these r theta and phi are not having constant directions as well always, as was the case with x cap, y cap, z cap. Depending upon where the point P is placed in space with respect to origin, these r theta and phi directions are going to change. So this dlr, that is the r component, is just dr along the r direction. dl theta is just r d theta, and dl phi is slightly complex. This is r sin theta d phi. We can also define a volume element d tau corresponding to this as a dlr into dl theta into dl phi. So that is similar to the volume element definition in Cartesian coordinate system, which was as dx dy dz. So this is just the product of these three terms. So it is going to be r squared sin theta dr d theta d phi. This is the volume element in spherical coordinate system. We can keep on exploring this system further as we try to use it. So this discussion is sufficient to just introduce it. Now for the cylindrical system, again we will draw the xyz axis as we drawn earlier, and then point P. This was R. Now what we do is we draw a normal from P on this xy plane, and similar to this R, we draw another line joining O and this point P dash, which is the projection of P on xy plane. Now this OP is called as S. So this forms one of the coordinates. So this can be lifted or shifted here. Just a minute. Just excuse me. Okay. And we can redraw this S at this place as well. So this is also S. Since this is S, the direction corresponding to line joining along this direction of S is going to be ds cap. Along with this, we define phi exactly in a similar way to the spherical polar system. Now the other coordinate is just this height z. This is how we define a cylindrical system: S, phi and z. Such type of system is advantageous when we try to use problems involving cylindrical surfaces. Now the relations which involve transformations from Cartesian to cylindrical system are x is equal to s cos phi. This is straightforwardly clear. Since this is s, its component along x is going to be s cos phi. Then y would be just s sin phi. The component along y for this s is going to be s sin phi, and the z component is just the z value, because it is the traditional Cartesian coordinate z, which we have already used many times. So these are the transformation equations which relate the cylindrical coordinate system with the Cartesian coordinate system. Similarly, we can define the line elements dls, dl phi and dlz. Now dls is just ds, as we have seen in this diagram. Then dl phi is s d phi, and dlz is just dz, which is the traditional case with the Cartesian system. Now we can also try to define d tau as dls, dl phi, dlz, the product of these three elements. It comes out to be equal to s ds d phi dz, that is d tau. Now, as a part of exercise, before that, as we can see now that S is similar to the R of the spherical polar system. So the limits on S are from 0 to infinity. The limits on phi are from 0 to 2 pi, as was the case with spherical system, and the limits on Z are obviously from minus infinity to infinity, as was the case with Cartesian system. Now, as a part of exercise, just try to find out the volume of a sphere. Volume of a sphere of radius r. So since this involves a sphere, we are going to use spherical coordinates. So volume element d tau is r square dr sine theta d theta d phi, and we can integrate this so to get the volume of the sphere. So integral of this is r square dr sine theta d theta d phi. R runs from 0 to capital R, which is the radius of the sphere. Phi runs from 0 to 2 pi, and theta runs from 0 to pi. These are the typical limits. So these limits cover the entire sphere centered at origin. So this is equal to integral r square dr from 0 to r, integral d phi from 0 to 2 pi, integral sine theta d theta from 0 to pi. Now this can be solved. Integral of this is r cube by 3 between limit 0 to r. Integral of d phi is phi between limit 0 to 2 pi. Integral of sine theta is minus cos theta between limits 0 to pi. Now this is just r cube by 3. This is going to be 2 pi since the lower limits are 0 in both the case. And this is minus cos pi minus of minus cos 0. Yes, so minus sign is sitting there, so we have to take into account that as well. So this is r cube by 3 into 2 pi into, now cos pi is minus 1, so minus 1 into minus is plus 1, minus combined gives us a plus, and cos 0 is 1. So this is nothing but equal to 2. So this, if we include this here, 2 into 2 becomes 4 pi. This divided by 3 r cube. So this is a very well known expression that volume of a sphere of radius r is 4 by 3 pi r cube.